coming from? Well, that's part of the energy that's in your thrust. Those water molecules right next to the fish are in contact with water molecules slightly farther away. And as they start to move forward, as the molecules in contact with the fish start to move forward, they're going to drag those other water molecules, which will drag other water molecules, etc., etc. That is your viscous or frictional drag. This tends to be relatively constant at different speeds and body shapes. But the way that you can minimize this, and the way fishes do over evolutionary time, is two ways. You can manipulate your shape, or you manipulate your surface texture. So for shape, let's just look at two broad categories of shapes. One would be spherical, and the other is going to be more cylindrical. So essentially we have a short, plump shape versus a long, skinny shape. And the one that is going to work best here is going to be our short, plump. In other words, that is going to have or create the least viscous or frictional drag. So if this is A and this is B, the volume of A equals the volume of B. So we have two fish of comparable size. We're just changing the shape of them. The fish with this shape will have less viscous or frictional drag simply because, anybody know?
It's small.
Surface area. Surface area is everything in biology. Sure, the surface area is less for a sphere than it is for any other shape. So it has less surface area, less of the fish is in contact with water molecules, therefore as it moves forward, it would pull fewer molecules with it. So that's how you could reduce it. Modifying surface texture. If you have a really rough surface, that could create more viscous or frictional drag. If you have a really smooth surface, you would have less drag. Just a rough, anything rough is going to create more friction than is a smooth surface. And so you do have some of your better swimming Actinopterygii that have very, very smooth surfaces. They have very tiny scales that do not extend out into the water. They're more, instead of overlapping, more one right in front of each other. Something like a tuna has a very, very smooth surface. Tunas are swimming all of the time. They're reducing their viscous or frictional drag by having a very smooth surface. Right? Inertial or pressure drag. As this fish moves forward, it's vacating its position in the water. All right, so let's say it was over here before, B. It's now over here, A. Where it was before was not occupied by water. Once the fish leaves, water comes in behind and fills that vacuum. Something has to provide the energy for that to occur. Well, in a sense, it actually is sucking the animal backwards. But that is your inertial or pressure drag. It is the low pressure behind the animal as it vacates that is essentially sucking the animal backwards slightly. If we look at shape again, we take our two shapes A and B in similar volume. In the laboratory, what you can show is that shape B is actually better than shape A to minimize inertial or pressure drag. So we have a conflict here. If you want to minimize viscous or frictional drag, you should be spherical. You should be short and plump. If you want to minimize inertial drag, you should be long and skinny. And it turns out that the best swimmers, this is true of marine mammals and it's true of fishes, they adopt a compromise shape that doesn't minimize that viscous drag, doesn't minimize inertial drag, but does minimize overall drag. How can that be? Well, if you look at, let's take the width versus the length of a fish. So the shape of a fish. I want to do total drag. And you look at total drag, so that would be summing viscous drag and inertial drag. The curve would look something like this. So 0.1, 0.2, 0.3, 0.4, 0.5. So we're taking the width divided by the length of the fish. That's what the curve for total drag would look like. And so our minimum is not at either end of the spectrum. Instead, our minimum is somewhat in between. That's where we find the shape of our best fishes, best swimming fish. And the shape that they have is called fusiform. I can draw this. Something like that, something like a teardrop shape, if you will, or sometimes described as a spindle shape. In these guys, the maximum width is something in the area of 1/4 of proportional, about 1/4 of the length of the animal. So that's the width from A to A. That's the length of the animal from B to B. If we take this width from A to A divided by the length and get it to be about 1/4, that gives us our spindle shape. That's where we find our best swimming animals, because it's that shape that reduces overall drag. It's a compromise. It doesn't give you the lowest frictional drag, it doesn't give you the lowest pressure drag, but it gives you the lowest overall drag for that animal. Just a couple of animals. A tuna is at 28%, sharks typically at 26%, dolphins 25%, swordfish 24%. So your fish that are constantly swimming adopt this fusiform shape in order to minimize overall drag. Oh, quick now or later. Okay, we'll do one more thing on swimming. We talked about the muscles. They're in these myomeres from front to back. Functionally, fish have what's called a dual motor system. In other words, they have two different kinds of muscle fibers making up those myomeres. And you can distinguish them by color very broadly. So we can have red fibers, and we can have white fibers. The bulk of the trunk muscles are white. Right? So that only a small portion, maybe up to 15% at most, are going to be red. So 85% or more are going to be the white fibers. Well, how do these things differ? Red, as usually is the case in biology and animals, if you have something that's described as being red, it's because it's well vascularized. Right? So well vascularized. And the white would be less so. So we have less blood going to those white fibers. Inside the fibers, inside the muscle cells of the red, we have an abundant amount of myoglobin. Anybody know what myoglobin does? Bind. Oh, troponin. No, you're talking about in the cell for contracting. Troponin and tropomyosin and all that. Yeah. No, but it is inside the muscle cell. That's the myo. But you also see the globin. It's